All right, okay, so what were we doing last time? We started our discussion of free convection, and particularly we talked about the boundary layer phenomena, and we did a similarity solution. We covered the similarity solution for a vertical plate, and the solution involved solving hydrodynamic and thermal boundary layer together. They are coupled because of this temperature term. This temperature term gave rise to, remember, to the buoyancy forces, the density variations, and resulting in buoyancy forces. Therefore, it was part of the momentum equation as well. All right, and then we obtained this solution right over here. And Nusselt number, this is the local Nusselt number. The average Nusselt number would be 4/3 times the local Nusselt number up until the corresponding position. And the solution, we describe the solution in terms of graphics, right? So this is the shape of the boundary, velocity boundary layer, and that's the shape of the thermal boundary layer. We said that any result that we obtain over here is also valid. If we say that, let's say that any result that we discuss over here, remember that the temperature of the plate was higher than the surrounding temperature, the ambient temperature. Therefore, we would have this upward boundary layer forming towards a vertical direction. It is on the opposite direction of the gravitational acceleration right over here. But what happens if we have a lower surface temperature? Is it going to be any different? No, it's not. When you look at the equations, you're going to see that the equations are symmetric if Ts is less than T infinity. And we would, if we consider the direction of a coordinate x like that, there is one particular aspect that might be puzzling. Notice that we defined the Grashof number as this temperature difference. We assume that increasing temperature density would decrease, so that would give us the upward motion. Now we are defining direction of motion in the direction of gravity, so everything is flipped. Therefore, you are going to notice that this delta t is going to be flipped if you go through and derive the same, same arguments. If you go through the same arguments, you are going to see that that's going to be T infinity minus T with the same convention. Therefore, the Grashof number is going to be defined as G beta T infinity minus Ts and L cube and so on. So we are going to flip the direction of temperature. Long story short, Grashof number is never negative. So is the Rayleigh number. They are not negative. You are going to calculate them based on the absolute temperature difference. You can simply put delta T there, and depending on the condition, you take the absolute value of that temperature and know by inspection which direction the boundary layer is forming. Hope that's clear. Okay. All right. So all right, so let's solve an example problem. Problem 9.7. Consider a large vertical plate with a uniform surface temperature that is suspended in the quiescent air, and it's an atmospheric pressure. The temperatures are known. We are being asked to estimate the boundary layer thickness at a particular location measured from the lower edge of the plate. I think you are hearing these, right? So let me move that a little bit down. That's probably be better also. Okay, what else? In part B, we are being asked the maximum velocity in the boundary layer at this location, and at what position in the boundary layer does the maximum occur. And in part C, using a similarity solution that we did, we are being asked to estimate the heat transfer coefficient, the local heat transfer coefficient at the same location from the lower edge. And then the question is, at what location on the plate measured from the lower edge will the boundary layer become turbulent? Okay, so first of all, you might be thinking, wait, we didn't cover, if you remember in chapter 7, we covered particular, expressions for boundary layer thickness, let's say friction coefficient, fanning friction coefficient, and so on. However, we didn't cover them here. How are we supposed to find boundary layer thickness? You might be puzzled. But we already have the solution in the graphical form, right? So we are going to use that. So let me bring an inset of the problem to the corner of my screen. And let me draw a quick sketch. Excuse me. Okay. All right, so this is a plate, and the temperature of the surface is greater than temperature of the air. Therefore, we are going to have, and here is T infinity, that's 25 degrees Celsius. We are going to have a boundary layer that is forming in that direction, right? What we are being asked is, if you consider our coordinate system X from the bottom lower edge of the plate, this turns out to be the leading edge of the plate, right? If you were being asked, if you know the dimensions of the plate, length of the plate, and the coordinate system was another way, you need to still, consider the leading edge of the plate for our discussion, for whatever we are using for Rayleigh number, Grashof number, and so on. Okay, and then therefore it is being asked, like there's a certain distance at a particular location. Let's call this location over here, that's x of 0.25 meter. And we are being asked at that location, what is the thickness of the boundary layer? What is the maximum velocity? And what is the y location? Y location such that this maximum velocity occurs, right? And here is the y direction. That's essentially what is being asked. Okay, so we are going to definitely need our fluid properties for that. It's air. So the fluid properties, we are going to evaluate the fluid properties unless otherwise is noted when there is boundary layer phenomena, right? We are going to evaluate the fluid properties neither at the surface nor at the ambient conditions. We are going to evaluate them at the film temperature. That is the arithmetic mean of those two temperatures. That is, I'm emphasizing because I believe that's the first time we are using this. Okay, so that's 350 Kelvin. And under those conditions, density of air kilogram per cubic meter, kinematic viscosity is 7.92 times 10 to the power minus 6 meters square per second. Thermal conductivity is 30 times 10 to the power minus 3 watt per meter Kelvin. And the Prandtl number is 0.7. We need one more property, one more thermodynamic property. Which one do you think is that? Is anyone awake? Yes, Burhan, thank you. It is the volumetric thermal expansion coefficient. And for air, assuming it's an ideal gas, it's not on the table because we don't need a table for ideal gases. It is the reciprocal of the temperature. Here we are evaluating at the film temperature. That's 1 over 350. And that's going to be 2.857 times 10 to the power minus 3, 1 over Kelvin, or Kelvin raised to the power minus 1. Okay. Oh, I wrote in a really inclined way. Anyway, okay, so next step is to calculate the Grashof number and Rayleigh number to identify what kind of flow characteristics we are looking at the point of interest, x is equal to 0.25. So let's calculate that. And notice that now the TS is greater than T infinity, so I'm using in the absolute value sense that's going to be positive, so I can write it that way. I'm always taking the positive temperature, positive value of the temperature difference. And that's going to be 9.81 times minus 3, the temperature difference of 130 minus 25, and the distance is 0.25 raised to the power 3 divided by 20.92 times 10 to the power minus 6, but this is the square of that. And then we obtain the Grasov number as 1.051 times 10 to the power 8. But it's not enough. Well, our formulation depends on the Grasov number. We still don't know. I mean, I'm solving this example problem right now, but if I solve this example problem after covering all the topics in this free convection chapter, we would have to ask this question, like, where are we? Like, are we in the laminar flow region or in turbulent flow region? Because in turbulence, we are going to have other correlations. So you need to identify, check the Rayleigh number to see where we are standing for this particular location. If you do this, simply multiply with 0.7, you are going to obtain 7.355 times 10 to the power 7. And that's clearly less than our threshold, the critical Rayleigh number, 10 to the power 9. Therefore, we can say that we are in the laminar flow regime. Great, so that means we can apply whatever we learned so far about the problem. That includes being able to use the solution of the similarity problem, similarity solution. Oh, I forgot to write probably in the previous class. That is from your textbook, figure 9.4, so you can refer to that. And now the question is, how are we going to use this figure? First thing is, estimate the boundary layer thickness at a location. That's x is equal to 0.25. What does the boundary layer thickness mean? It is actually the location at which the velocity, by the way, you are talking about the hydrodynamic boundary layer here. So the velocity is going to approach zero near the edge of the boundary layer, right? So when we look at this graph, first of all, there are individual trends for the particular Prandtl number that we are interested. So this is approximately 0.7. So I'm going to use this trend over here. And when you look at this trend, the velocity profile is approaching 0 around eta is equal to 6. So in other words, we are interested in y is equal to delta. When will this happen? When our similarity variable eta becomes 6. So here we go. This is our actual gateway to obtaining a boundary layer thickness. What is the definition of eta? Y over x multiplied by the Grasov number divided by 4 raised to the power 1/4. And if you substitute delta over here, we can write this as delta over x. Grasov number divided by 4 raised to the power 1/4 is going to be equal to 6. From here, you can solve and obtain an expression for delta for this particular Prandtl number. So that's only valid for Prandtl number of 0.72. But if you look at the other Prandtl numbers, for instance, as the Prandtl number goes to 10 or 100, it is getting closer with delta. This eta is becoming like around 5 or maybe 4.5. But otherwise, you're in the same neighborhood. So you can infer about that. So delta is equal to 6 times 4 over Grasov number raised to the power 1/4 multiplied by x. When we substitute the numerical values, that's going to be 6 times 4 over 1.051 times 10 to the power 8 raised to the power 1/4 multiplied by 0.25. Anyway, okay, so we obtain a boundary layer thickness of 0.021 meter. So let's visualize that. Under those conditions, within 25 centimeters of distance like that, we have a boundary layer thickness developing about 2 centimeters, something like this, right? So you can visualize that. This is part A of the problem, and that's the result for part A. Let's take a look at part B. In part B, you are being asked, what is the maximum velocity in the boundary layer at this location, and at what position in the boundary layer does this maximum occur? Again, we are going to take a look at this. I think I already put a line over there. Let's take a look. All right, so this maximum location, let me erase that. This is the maximum location we are looking at. This maximum location approximately corresponds to eta is equal to 1. And if you go ahead and read from the other axis, notice that that's a derivative of f, and it is related to the velocity here. So this is some measure of maximum velocity right over here. It's linearly proportional. So we can retrieve that. So from this plot, it is about 0.275. I'm reading it by my eye. We are doing something similar to what we did with the Moody chart, or even back in 311, we would read fin efficiency from the plot. So that's the same thing we are doing. Okay, so we have Prandtl number is equal to 0.7. Conditions are laminar, and the location is location doesn't matter in that, right? Because it is a function of x right over here. So this is actually collapse for all different values of x into a single curve. So this is enough. So we are going to read from the chart as u is equal to u max at eta is equal to approximately 1. And when eta is equal to 1, and f prime eta, that's equal to u max multiplied by x divided by 2 nu multiplied by the Grasov number raised to the power 1/2 minus 1/2 is going to be 0.275. Based on that, we can calculate u max. We can solve for u max and calculate it as 0.275. That's even worse. There we go. 0.275 times 2 times 2.92 times 10 to the power minus 6 times 1.051 times 10 to the power 8 raised to the power 1/2. And that's going, oh, this is divided by 0.25 because of x star. And from here, you obtain u max as 0.472 meter per second. So at this particular location, within this thick boundary layer, some part of this boundary layer, the fluid is moving at a particular location with 0.5 meter per second. So it is something like this. Right? So you can visualize that a temperature difference of approximately 100 degrees Celsius here is causing that kind of flow phenomena. It's very interesting. Okay, so this is what there is one more question. What is the location of across the y-axis? What is the location? So eta is equal to 1. We can go ahead and do the same calculations, saying that at this particular y, eta is equal to 1. However, notice that eta is linear with respect to y, right? So therefore, if we were to say that when eta is equal to 6, we obtain delta as that or y as that, we can say that when eta is equal to 1, the y is going to be 1/6 of that. So I don't think you will be any puzzled when I wrote delta over 6 over here. That's going to be what we obtained previously divided by 6. That's 0.0035 meter. That's the particular location I meant. That's from the surface where this velocity occurs. Okay. All right, the last part, I'm sorry, it's part C. We have two parts. So in part C, we have being asked to use a similarity solution to obtain a local heat transfer coefficient at this particular location. We are going to start by considering the Nusselt number. That's going to be Grasov number divided by 4 raised to the power 1/4 multiplied by this particular function of Prandtl number G. And we can directly calculate G based on its description. We know that its description is right over here. I'm not going to write it down again. It's a lengthy expression. That's the description of the Prandtl number function G. And I will substitute the numbers. And denominator is 0.609 plus 1.2 to 1 times 0.70 raised to the power 1/2 plus 1.235 times the Prandtl number again. And this is all together raised to the power 1/4. It's a kind of complicated expression that doesn't really have much meaning in it. It's simply calculations, right? Not much interpretation there. Okay, so this is the number we get from this function. Therefore, when you can calculate the Nusselt number as 1.051 times 10 to the power 8 divided by 4 raised to the power 1/4 multiplied by this. And this is going to be equal to 35.72. And from here, we can calculate h. That's the local h at that location, particular location. I might drop this x, right? So it is really to emphasize that that's local convection heat transfer coefficient. That's going to be Nusselt multiple. I can also drop the x from Nusselt. It doesn't make much sense. And that's going to be 35.73 times 3 divided by 0.25. So what we obtain as h is, what value do you think? In the previous, when we were solving example problems in internal flow, we obtained h values like thousands or even 10,000, something like that, right? But here we obtain h values on the order of 5, at most 10, if not less. So free convection is quite weak in actually facilitating heat transfer. That doesn't make it less important than forced convection. A lot of things happen in free convection. Like once we don't have forced convection, what we have in our disposal is free convection. That's the way a lot of power systems are cooled down in let's say in external space, like in ambient temperature, right? So that's watt per meter square Kelvin. Even though convection coefficients are low, that doesn't mean that they are insignificant. They are the main driving force, main driving effect for heat transfer for many applications. Okay, so there was one more part. It's the onset of turbulence being asked. what is the location at which we are going to have onset of turbulence? Remember that. So just like the force convection over a flat plate, after some distance, there's going to be disturbances in the flow. They're going to get amplified and result in transition to turbulence. And we identified that aspect as we outlined in the beginning of our solution. We said that that's actually the location x critical. That's going to be, oh, excuse me, 10 to the power 9. And that's essentially will give us a way to obtain it's multiplied by the Prandtl number. Or what you can write is, instead of that, the definition of the Rayleigh number, you can also write it like that, right? So let me actually write with the Prandtl number, because that's what we obtained from the tables. And that's going to be 10 to the power 9. And therefore, I substitute the numbers 10 to the power 9 times, oh, there is a square here, don't forget that, times 10 to the power minus 6 squared divided by 10 to the power minus 3. And this is multiplied by the temperature difference of 130 minus 25. So, and this is all raised to the power 1/3 because of this 1/3 power. And as a result, we obtain the critical position as approximately 60 centimeters from the leading edge. That's the bottom edge of the plate. Okay. Any questions for this example problem? Let's remember and make sure that this solution that we obtained here, this particular solution is valid for laminar free convection over a vertical plate. That's a very specific condition. But vertical plates, we can have turbulence as well. And in general, for turbulence, we rely on empirical correlations. And when people are developing empirical correlations, they also went into trouble of generalizing those into the laminar flow as well. So instead of the similarity solution, remember that when we had laminar conditions in forced convection over a flat plate, we used the Blasius solution, which gave us this Nusselt number, average Nusselt number of 0.664 Reynolds number, Prandtl number, if you remember. So this was the similarity solution. But in free convection, people actually correlated laminar flow regime as well. So let's talk about some empirical correlations. Okay, so in general, when you look at the empirical correlations of immersed bodies, we are going to see an expression looking like the average Nusselt number is going to be equal to some constant multiplied by the Rayleigh number raised to the power n. That kind of power law we are going to be seeing. And under those, this is general. This is the general form of the simplest correlations we are going to see for the cylinder. We're going to see for vertical plate here. For instance, for vertical plate, the coefficients are going to be 0.59 and n is equal to 1/4. These coefficients allow this expression to correlate really well for laminar flow within the range of 10 to the power 9. That's, in other words, within the laminar flow regime. Okay, so what else you can have? 0.10 and n is equal to, let me move this a little bit up though. I will need that space. Yeah, more to come. And n is equal to 1/3. And these are for the Rayleigh number range of 10 to the power 9 to 10 to the power 13. Clearly, we are now talking about the turbulent conditions. Okay, so these are, simple forms, but Churchill and Chu went into trouble of correlating the whole range, and they obtained this. That's due to Churchill and Chu. That's not how you write Churchill. That's a U there, Churchill and Chu. And this is for both laminar and turbulent conditions. And then they also went ahead and say that, you know what, for laminar conditions, we can actually fine-tune this correlation and obtain another correlation. That's for laminar flow. And for all those correlations, we are interested, the correlations were developed based on constant surface temperature and properties temperature properties evaluated at the fin temperature. Okay. At this point, I can hear the questions coming from the people who are awaiting the class. All right. Okay. So they are asking, okay, but what is the difference between those correlations? I mean, we have here 4 different choices to use for laminar flow, right? Similarity solution, this one right over here, this one here, and we got 2 different options for turbulent flow. Let me compare this one, and the similarity solution at least, right? Let's take a look at how different they are. That's not in your textbook. I actually plotted these correlations to comment on various things. So you can see over here that equation 9.21 is the similarity solution. It's the gray line, the gray solid line, and the 2 equations we introduced are blue and dashed orange lines. First observation is that as we go towards the 10 to the power 9, not even coming to the 10 to the power 9, but a little less than that, around 10 to the power 7 and 8, we are actually seeing that there is this deviation of the blue curve upward. And that's true because this is actually accounting for the enhancement of heat transfer due to turbulent flow, right? Therefore, this part of this correlation should not be used. The gray lines and orange ones, we cannot use them because we are in the turbulent flow regime. This correlation is for laminar, and the other similarity solution was clearly for laminar. So they're actually, maybe I can use some different color coding here. This part. So we are going using blue here. In the mid-range Reynolds numbers, the correlations are providing us results comparable. And notice that over here, this similarity solution is looking like that. However, when you do experiments, you're obtaining something different. That's because when you have flow velocities decreasing, then the conduction within the axis of the flow, meaning in the streamwise direction across x direction, becomes significant. When we were deriving these boundary layer approximations, boundary layer equations, we assume that the dominant mode of heat transfer across the flow would be by advection. We didn't consider conduction, and therefore the similarity solution, the assumptions for the similarity solution are becoming invalid as you go lower in Rayleigh numbers. However, notice that these 2 correlations are quite matching. these two correlations are matching. That was the blue line. The other one was, do I have a orange here? I think I do. It's the dashed line. Hopefully I can go back to my original color. There we go. Okay. So when you look at over here, they are comparable. They are delineated the same way, but turns out that equation 9.37, this one over here, is the one that is specifically correlated for the laminar flow regime. It is slightly different. And notice that when I say slight, this part over here, that it is deviating from the others, that slight is a lot because that's a logarithmic axis. We are talking about a couple of folds of difference actually here. So therefore, that's what we would like to use. That's equation 9.27 for small Rayleigh numbers, right? So as a result, I think even though we derive the similarity solution, and it's great that we can infer about the particular thickness of boundary layer, what happens at what location and so on, that equation is very powerful. Here we are only getting the Nusselt number. However, for obtaining the Nusselt number, it turns out that this correlation is the way to go, right? Does this make sense? For laminar flow I'm talking about. And for turbulent flow, I would recommend you to go ahead and use this correlation 9.26. Hope that's clear. That gives you at least some direction on which correlation is optimal for the various conditions of the vertical plate. Okay. Hope that's clear. Okay, so the other thing we discussed was that these correlations are for constant surface temperature. We can have an electrical component that's being heated by uniform heat flux, right? It can be a power system, again, that can be heated inside by the electrical circuitry. Then we will talk about heat flux that's constant across the board. And how are we going to cool that down with natural convection when you don't have no means to actually induce flow within the enclosure, let's say, or it's simply open to the atmosphere like that, vertically. Okay, so under those cases, we can still use those correlations, it turns out. However, we need to do some extra work to actually make it useful. These correlations can also be used. I'm continuing what I actually, my stars, right? So these correlations can also be used constant heat flux conditions. However, notice that things are a little bit complicated because our governing dimensionless groups include delta T in them. You need to define the delta T, that's Ts minus T infinity or vice versa, as the location. So that temperature is going to depend on X direction in that case. And we are going to pick the location of temperature at the middle of the plate. That's equal to delta T, I'm sorry, that's equal to Ts at L over 2 minus T infinity, or vice versa, is used for calculation of Rayleigh number and Grashof number as well. And also, we are also using that in Newton's law of cooling. It will look like this. So convection heat transfer coefficient is going to be the heat flux divided by delta T L over 2. So how is this useful? I mean, if you know the heat flux, we already know the amount of heat transfer from the surface, right? And what becomes important here under those applications is the temperature operating conditions. So is there a limiting temperature? Like there's going to be hot spots on the surface, like there's going to be a location where the temperature is going to be greatest. Which location is that going to be? It's actually going to be the location where the boundary layer is the thickest, and it's going to be the trailing edge of the plate, if any. Or you can be interested in at any location on the plate, what's going to be the surface temperature of the plate at that location. Therefore, it is interesting that we can actually look in that. So this is an interesting quantity. In order to obtain this temperature as a function of location across the plate, we can actually do kind of an proportionality analysis, right? So let's, considering our reference temperature as delta T at L/2, let's now consider one simple correlation for a Nusselt number. It is C Rayleigh number raised to the power 1/4, right? This is the one for the laminar flow. And from here, you can see that when you write the Nusselt number in terms of H, and other side, you are going to notice that when you look at the decomposer Rayleigh number, it's going to be, Rayleigh number includes the delta T, and this delta T, hold on a second, that's not 1/4. Okay, so this delta T is going to be raised to the power 1/4, and let me write it proper. There's also going to be a length scale, let's say across a distance x, that's happening, and that's raised to the power 3, now 1/4 of that 3/4. So if you rearrange the terms, notice that this is a constant, so you can relate delta T and x to each other. Delta T raised to the power 5/4 is going to scale it x raised to the power 1/4, and the delta T is going to therefore scale it x raised to the power 1/5. So that's a simple proportionality. And then delta T, I would like to emphasize that that's at a particular x location divided by, at that particular x location, that ratio should be equal to our reference conditions, right? So delta T at the middle of the plate is going to be with the same proportionality with respect to x is equal to L/2. And if you rearrange the terms, you are going to see that this delta Tx is going to scale with this reference temperature difference middle of the plate multiplied by 1.149 times x over L raised to the power 1/5. Your textbook is actually using a less number of significant figures. They are using 1.15. So that's what your textbook is using. But you can see where it is coming from now, right? It is 2 raised to the power 1/5. Okay. So this way, we can actually obtain the temperature variation across the plate based on the temperature difference at a particular location of the plate. Any questions?
Hocam, could you go to the previous slide?
This one?
Yes, hocam. What is the reason for like the equation 9.2 and 1 we obtain it from similarity solution? What is the reason for it not to be like accurate as the other equations, considering the low Rayleigh number region?
Okay, so there are two crosses here. So I think this part is pretty clear because this is beyond, it's Rayleigh number increasing and we are entering to the turbulent region, right? So laminar flow conditions are no longer valid. Actually, we are saying that this Rayleigh number 10 to the power 9 is turbulence, but there's a transition region as well, just like with the internal flow where we said that Reynolds number of 2300 is the limit, but then the fully turbulent flow is at Reynolds number of 10,000. Similarly here, we are going to have a range where the laminar solution is going to gradually become inaccurate. So you can see that deviation between blue line and gray line, and that's exactly why it is. So this part, don't use the similarity solution. Clearly, it's for laminar flow. That's a complete violation of the assumptions here. This part over here, we didn't really, give you any details on that, but you can infer that with the Rayleigh number decreasing, that's essentially corresponding to the speed of the flow being decreasing. Right, so we actually, when we were first defining Grashof number, we said that's the square of the velocity scale of the laminar flow. And if you consider this, when the Grashof number and Rayleigh number decreases, we are going to have lesser speed in the flow. When the speed of the flow decreases in the axial direction, that means the flow, the energy is not carried by advection alone anymore. The conduction effects across the axial direction of the flow. I think I have a graph. Let me show you over here. So as this velocity diminishes, the energy transport across this vertical direction is no longer by advection only. That's one of the assumptions that we make in boundary layer equations, approximations. So therefore, since we are solving boundary layer equations, this assumption is embedded in that. So this assumption is violated for small Rayleigh numbers, and therefore this part is not accurate. It's simply a mathematical formulation. When people do experiments, they see that as the Rayleigh number decreases, the boundary layer approximations become gradually inadequate, and therefore the actual trends from the experiments for laminar flow is actually showing this. And the distinction between those two curves is simply because equation 9.27 is particularly correlated for small Rayleigh number regimes. So it is the ground truth for us. And that's why I said, use that equation 9.27 for laminar flow. Does this make sense? I think that was a lengthy explanation.
Clear, Roger.
Okay,
I thought
great.
it has to do with the assumptions.
Okay, it was actually about the assumptions, and yeah, this boundary layer approximations becoming invalid for small Rayleigh numbers. All right, so with that question, maybe I think it's a good time to take a break. Once we come back in 10 minutes, let's say 9:40, we are going to discuss some other configurations, geometric configurations.